Hello, everyone. My name is Lester Mackey, and today I'll be presenting Online Learning with Optimism and Delay. This is joint work with a number of excellent collaborators, Genevieve Flaspohler, Francesco Orabona, Judah Cohen, Sukaina Muatadid, Maruna Opresco, and Paolo Orenstein. So this is a talk about online learning, a popular paradigm for sequential decision-making. Each day, the online learner makes a decision, WT, suffers a loss for that decision, we'll call that LT, and then uses that loss function to improve future decision-making. Now, this is also a talk about optimistic online learning. And in this variant, before making a decision, the learner gets to observe a hint about the future loss function. And this is especially useful when the future is somewhat predictable. You can think of this as an estimate of the LT that has not yet been observed. Okay, so what's the goal of all of this? Well, our goal is to perform nearly as well as the best constant decision in hindsight. And the way that we measure that is with a quantity called regret. That's the difference between the total loss of the online learner and the total loss of the best constant decision in hindsight. Okay, so why do we care about this? Well, lately my collaborators and I have been developing forecasting approaches for subseasonal climate forecasting. That's predicting temperature and precipitation 2 to 6 weeks in advance. And these forecasts can be issued daily, weekly, or semi-monthly. And over time, we've been developing a diverse collection of forecasting models. We find that in any given year, any given period of interest, say a year's time, at least one model performs well, but it's typically unclear which is going to perform the best a priori. So our goal each year is to produce a series of real-time forecasts that perform nearly as well as the best single model in hindsight. So this might seem like a perfect fit for online learning. Here, the regret is the difference between our real-time forecasting loss and the total loss of the best single model. So this is a promising approach, but it also has a number of challenges when we think about deploying it in practice. First, real subseasonal forecasting has delayed feedback. You actually have to issue multiple forecasts before you receive any feedback about your first forecast. You also have short regret horizons. So when we're producing semi-monthly forecasts, you're only going to get 26 pieces of information over the course of a year. But we still want to achieve small regret in that short time frame. And then most online learning algorithms have hyperparameters, and the standard settings for those parameters are somewhat impractical. They're often based on worst case future losses, and setting them in this way is either challenging to implement or overly conservative. So what I'd like to do in this talk is introduce a few new algorithms, 3 new algorithms in particular that provide optimal regret under delay and can handle even variable and unbounded delays, that incorporate hints, not just for the future, but also for the missed feedback that's caused by delay, and use this to mitigate the impact of delay, that have no hyperparameters to tune, and that can be used with a new learning to hint wrapper to learn effective hinting strategies. Okay, let's get into it. So first, let's review a couple of standard online learning algorithms. The first we'll consider is called Follow the Regularized Leader, or FTRL for short. In FTRL, you produce each decision by minimizing a sum of linearized losses plus a strongly convex regularizer, convex with respect to some norm. Here, the term G1 through T that I've written represents a sum over all of your losses, but not of the exact losses of a linearized form of those losses. We linearize each loss by looking at a subgradient of that loss. So G1 through T is a sum of those subgradients, and the inner product with W gives you your linear approximation to the sum of all the losses that you've observed so far. Meanwhile, lambda times psi provides your strongly convex regularizer with a regularization parameter lambda. Okay, that's FTRL. The second standard algorithm we want to consider is called online mirror descent. In this case, you choose each decision by minimizing just the latest linearized loss. So you take the latest subgradient, GT. But instead of just optimizing that, you also want to stay close to your last decision point. And the way you measure closeness is with respect to a Bregman divergence. So giving the definition of a Bregman divergence here, common example is just squared error. And that's being induced by your strongly convex loss function psi. Okay, so those are online learning algorithms. Now we're going to imbue them with optimism. First, we're going to consider optimistic FTRL, proposed by Rocklin and Sridharan. The idea here is that instead of just optimizing over your observed loss subgradients, you also incorporate a hint vector. The hint now is going to come into the form of a guess at what your future subgradient might be. So you have a hint vector, we'll call it G tilde T plus 1, and you can see that you can view it as an estimate of the future feedback, G T plus 1. The benefit here is that you get reduced regret whenever your hint approximates that future unobserved subgradient well. Similarly, we're going to imbue our online mirror descent algorithm with optimism. For that, we're going to use a particular form of optimistic OMD which we'll call single step OMD or SUMD. And this is proposed by Jelani et al. So just like in FTRL, we're going to introduce an extra hint term. Here comes in the form of the difference between today's hint and yesterday's hint. Okay, so now we have some optimistic algorithms, but this is a talk about delay. So how does delayed feedback fit into the picture? Well, when you're doing online learning with delay, the problem is you don't actually observe the loss on the play that you just made. So I make my decision WT. Instead of observing the loss for that play, I observe the loss for some previous decision. I'm going to call that the T minus Dth decision. So D now represents the amount of delay. Throughout the talk, I'll just assume a fixed delay, a constant delay of D, but you can check out our paper to see how you can deal with variable and unbounded delays. Okay, so I make my decision. I observe the loss that I incurred D time steps ago, and now I still have access to that stale loss function to improve my future decisions. But this is somewhat problematic because those algorithms that I just showed you, the two optimistic algorithms, rely on immediate feedback, and so they're currently unimplementable. The feedback that they require is not yet observable because of delay. So what can we do? Well, a natural thing to do is to modify your algorithms to just make use of the gradient information that we have available. And so we're going to consider two optimistic delayed algorithms. The first is optimistic delayed FTRL, odd FTRL. It just differs from optimistic FTRL in that we only use the sum of subgradients observed so far. Here we still have a hint vector, but I have changed the name of the hint vector. So now it's called H. And I've done this on purpose because whereas in typical optimistic online learning, your hint just represents a guess for the next feedback you're going to receive. Now we're going to use our hint in a different way. We're going to use it to estimate our future hints. We're going to use it to estimate our future feedback, but also the missed feedback, the feedback that we missed due to delay. Okay, we're going to do the same for OMD. We're going to introduce delayed optimistic OMD. We're going to call that doomed for short. And instead of using GT, instead of incorporating GT into your objective, we're just going to use the last observed subgradient, which is GT minus D. All right, so how do these algorithms perform? Well, our first insight into these algorithms is that learning with delay for doomed and odd FTRL is actually a special case of learning with optimism. To see what I mean by this, consider the following lemma. It says that optimistic delayed FTRL is just an instance of optimistic FTRL with a really bad hint. A hint that just deletes the last D observations. Interesting. And the same thing is true for doomed. Doomed is just a special case of zoomed, optimistic OMD with the same really bad hint that just deletes the last D observations. And it's worth digging into like why this happens. So zoomed, if you look at the zoomed algorithm, the optimistic OMD algorithm, it only depends on the gradient GT and the hint G tilde T plus 1 through a sufficient statistic, the sum of all the gradients and the hint. And in the case of our really bad hint, this sufficient statistic, this sum is observable, even though GT and GT and G tilde separately are not observable. Now, this isn't true for every algorithm. In particular, this property is not satisfied by the more common two-step optimistic OMD algorithms that have been proposed in a number of different papers. So this is roughly what those algorithms look like. They imbue online mirror descent with optimism in two different stages. And the problem with these algorithms from our standpoint is that they rely explicitly on GT, which is a quantity that's unobserved. Okay. So what value is this reduction? Well, this delay-as-optimism reduction tells us that any regret bound we can derive for optimistic learning immediately implies a regret bound for delayed learning. So let's start by considering a new guarantee that we've derived for optimistic online learning. Here's the theorem. It gives you a bound on the regret of optimistic FTRL. And you could do the same for optimistic mirror descent. Let's unpack this a bit. The bound is in terms of this Huber function. That's the standard robust Huber function. And what's the property of this function? Well, first, this Huber term is going to be 0 if your hint is perfect. So if you give a great guess about the future, that sets that regret term to 0. It grows quadratically when your hint error is small, and then it grows linearly when your hint error is large. So this actually strictly improves past optimistic FTRL guarantees, which basically just have quadratic growth. And simultaneously, it demonstrates this added robustness in accurate hints. And that's going to become very important when we start applying these results to delay, where our hints could be quite bad. And the same actually holds true for our optimistic mirror descent guarantees. So combining this theorem with our delay-as-optimism reduction, we immediately get the first general analysis of delayed follow the regularized leader. That's with or without optimism. But please see the concurrent work of Shea et al., which deals with delay but not optimism. Okay, so here's the result. It looks very much like the past result, but let's unpack it a bit. Like what do we see here? Well, first, we see a compounding of regret due to delay. So these BTF terms, they correspond to those Huber functions. In the worst case, they have size d plus 1. And that means when we pick the optimal lambda parameter, when we pick the optimal regularization parameter, our regret is going to have size square root dt. Now, on the one hand, that is known to be rate optimal in the presence of delay. That's minimax optimal. That's optimal in the worst case in the presence of delay. But on the other hand, that should give us some pause, because it says that delay has a multiplicative impact on our regret, and so it could potentially lead to a much worse performance. But all is not lost. This theorem also highlights the heightened value of optimism in the presence of delay. So what do we see? Well, we see in this Huber loss function that we can mitigate the impact of delay by giving a good hint, and by giving a good hint not just for the future, but also for the past subgradients that were missed due to delay. So if, now my hint wants to target the sum of the subgradients from time t minus t up through t. So that's great. And that suggests a strategy for setting our hints in the future. This result also strengthens the analyses of several special cases that have appeared in the literature. In particular, the bounds that we get are in terms of a norm of a sum over gradients. Many prior results are in terms of the sum over norms, and that can actually lead to a big gap in practice. When you're not in an adversarial worst case setting, the average of these sums might only grow like square root d instead of d. I also want to point out the prior work of McMahon and Streeter, which is for specifically unoptimistic scalar, that is univariate online gradient descent. Okay. So we have some algorithms, we have some guarantees, but these guarantees depend on the regularization parameter lambda. So how do we pick that in practice? Well, the ideal thing would be just to optimize our regret bound. But of course, that leads to a lambda parameter that's unobservable. It depends on gradients that we haven't yet encountered. So as an alternative to this, I'm going to offer up two practical strategies. First, we're going to consider a pair of tuning-free algorithms that are actually completely independent of the setting of lambda, and hence also optimally tuned with respect to lambda. And then we're going to explore a self-tuning strategy called AdaHedgeD that adaptively sets lambda in a near optimal way. Okay, first, tuning free. To reach our algorithms, we're going to start with two popular strategies for optimizing on the simplex. The first is called regret matching due to Blackwell in 1956, and was developed for finding correlated equilibria in two-player games. These are what the updates look like. The second algorithm is called regret matching plus. This was it was designed as an improvement for regret matching and has been used to essentially solve the game of heads up limit Texas Hold'em poker. Both algorithms are known for their strong empirical performance. In each case, the plays, the decisions, WT that are being made lie in the simplex. So you could view them as a convex combination of input model forecasts. But for our purposes, there are some problems. First, the algorithms don't naturally accommodate delay or optimism. And second, the known regret guarantees for these algorithms are suboptimal for large D, that is when you have a large number of input forecasts. So we'd like to address both of these deficiencies by modifying these algorithms. First, let's imbue both algorithms with both delay and optimism. To do this, we're just going to replace all the RTs you saw, the GTs and RTs you saw, with T minus Ds. We're only going to use data up to that's been observed so far. That's roughly what we did before. In addition, we're going to add in optimism in the form of a hint vector H, just as we did before. Now, to deal with this dimension dependence, I'm going to make one further modification. I'm going to add in a new parameter Q, and later on, I'm going to show you how to choose that Q explicitly and very easily to obtain optimal dependence of regret on the dimension D. Okay, so now the algorithms we produce, which I call delayed optimistic regret matching, DORM, and DORM plus for short, you can view as generalizations of regret matching plus, and also a generalization of the recent undelayed optimistic regret matching algorithm of Farina et al. All right, so these algorithms might look a bit complicated, but they actually satisfy a number of remarkable properties that I want to walk us through. First, the DORM and DORM plus iterates that we just introduced are actually just special cases of the optimistic delayed FTRL and mirror descent algorithms that we discussed earlier. Specifically, you can make this reduction by considering optimizing on the positive orthant. So take your W set to be a positive orthant, using a regularizer, which is the squared P norm, and using a special surrogate loss. This reduction means that we immediately get a regret guarantee for both DORM and DORM plus. Here's an example for DORM. We get the same sort of Huber regret that we were investigating earlier. Second, these algorithms are also independent of the choice of lambda, which means that I can run them with any value of lambda I want, say lambda equals 1, and I get an algorithm that is automatically optimally tuned with respect to lambda. That is amazing. And so let's see how this impacts our regret guarantee. Instead of just having a single lambda here, I can actually take the infimum over lambda, and I get back the optimally tuned regret without having to pick any special value of lambda. Fantastic. Finally, I mentioned that we have this Q parameter for a good reason. And this last version of our corollary says that if you pick Q in a certain way, there's a very simple setting of Q based on your dimension, you'll get back the optimal dimension dependence, that is a square root log D dependence on dimension for our algorithms. Great. So that's DORM and DORM plus. Now I'd like to explore a second strategy for dealing with hyperparameter setting. Instead of using a tuning-free algorithm, we're going to learn how to set lambda adaptively and automatically. To do this, first we have to understand what are the regrets. What's the regret of an algorithm that uses an adaptive setting of lambda? And so the algorithm we're going to consider we'll call optimistic delayed adaptive FTRL. And it's just like the optimistic delayed FTRL that we saw before, but now we have a time varying regularization parameter. So what does the regret of this algorithm look like? Well, here's a result from our work. It's similar to what we've seen already, but a little bit more complex. So let's unpack it. We again see a robustness to hinting error that we get from this robust Huber loss in the BTF terms. And we also see a potential to mitigate the impact of delay using accurate hints in this term. So that's great. Again, this has the property of improving past bounds in the literature. So we're not aware of other work that covers both optimism and delay, for general FTRL, but there are past undelayed bounds and past unoptimistic bounds, and both are improved by the guarantees in this theorem. And then finally, I want to highlight these new factors ATF that didn't appear in our past theorems. These bounded domain factors are going to enable practical lambda T tuning strategies under delay that are going to allow us to avoid having any prior knowledge about unobserved subgradients. And that's going to be important in practice because quite often you might just rely on a uniform upper bound on your subgradients or losses, but that can be very conservative or just difficult to compute. Okay, so coming to that point, how do we actually pick this regularization sequence that we've introduced? Again, the ideal strategy of trying to optimize your bound is impractical. It's actually infeasible because the gradients that you would need are unobservable. The standard approach is to take the terms in that bound, take the terms in this ideal setting that are unknown and then uniformly upper bound them. But in practice, that leads to very loose settings of lambda, or impractical settings that require a lot of prior knowledge. Instead, our approach is going to set lambda based on a tighter regret bound underlying the proof of this theorem. So we call this setting AdaHedgeD. And I'm going to spare you a lot of the gory details, but suffice it to say that we set lambda to be a sum of terms that are regret bounding that depend only on prior observations of our subgradients and hints. And given that setting, here's the sort of result that we can prove. What are the big takeaways? Well, first, we again get this rate optimal delay dependence, the square root dt delay dependence in the worst case. So that's great. The regret that we get on top of that nearly matches the optimally tuned regret bound in hindsight, even though we're setting these lambda parameters adaptively. Importantly, the setting of lambda doesn't require any prior knowledge of future subgradients, so we're not going to use any of these loose upper bounds on future gradients. And you can also view this as a generalization of the popular AdaHedge algorithm, but it differs in several important ways and incorporates delay and incorporates optimism, and it uses tighter regret bounds that we use to mitigate the impact of delay. Okay, so now we have our algorithms. let's turn to our application, subseasonal climate forecasting. So to give you a picture of what I mean by subseasonal forecasting, I'd like to think about the spectrum of weather and climate. So usually when we think about weather forecasts, these are very short-term forecasts, maybe anywhere from 1 day to 10 days out. And a 1 day weather forecast is usually pretty good, but I think as we've all seen, the weather forecast gets, the quality of the forecast plummets as we go farther out. And this is largely due to chaos involved in the weather forecasting process. On the other extreme, we have climate forecasts that are predicting temperature and precipitation, say, over months or seasons, years, decades, and beyond. And you're often getting a bump in forecasting accuracy simply because we're averaging over more time. So it's a less noisy target variable. But somewhere in between are what we call the subseasonal forecasts. These are roughly about 2 to 6 weeks out. And for subseasonal forecasts, the weather models aren't very good. The climate models aren't yet good because we're not averaging over enough time. And what happens, the observations that we're trying to predict depend both on local conditions, the local weather today, and global factors like sea surface temperatures around the globe, making it a complicated problem. So for the purposes of this talk, we'll say subseasonal forecasting means predicting temperature and precipitation 2 to 6 weeks out. Why do we want to do this? Well, it's important for allocating water resources to farmers, for managing wildfires, preparing for wet weather extremes like droughts and floods. And it has applications, an increasing number of applications to crop planting, irrigation, and energy pricing. And on top of all of that, in the past couple of years, there have been a number of competitions around improving subseasonal climate forecasting. And they've been called the Subseasonal Climate Forecast Rodeos. These rodeos were put on by the US Bureau of Reclamation, which is a government agency that manages, develops, and protects water in the Western United States. They're responsible for managing 17 states' water. They are the second largest hydropower producer in the country, and they provide irrigation water for 10 million farmland acres. And they note that over the past 8 years, every state in the Western US has experienced drought in a way that affects both the local economy and the national economy. And so they're hoping to improve subseasonal forecasting to better anticipate these sorts of extreme conditions. So they're interested in 4 forecasting tasks in particular: predicting average temperature and total precipitation over 2-week intervals, and at 2 different outlooks: weeks 3 and 4, and weeks 5 and 6. These forecasts are issued on a 1 by 1 degree latitude longitude grid across the Western US. So that corresponds to these 514 blue grid points in this display. And forecasts are issued every 2 weeks. And we're particularly interested in how well one does over the course of a year. So that corresponds to T equals 26 forecasts in our regret period. So I just want to give you an example of what a forecast looks like. Here I'm showing you a temperature forecast that we produced in 2018. Here's the ground truth in the top right. The top left is our forecast. In the bottom left, I'm showing you the forecast produced by the United States operational subseasonal forecasting system. You can see in this case, it's doing a pretty terrible job. Red here means hotter than expected. Blue means colder than expected. And basically, the operational model CFSV2 is just predicting cold where it should be predicting hot. Here similarly is an example of a forecast for precipitation, where brown represents drier than expected, blue represents wetter than expected. And here's in the top left is a forecast that we produced. On the bottom left is a forecast produced by CFSV2. You can see that both of these forecasts are actually pretty bad. We're getting some signal in the Texas region of rain, but largely both are just far too dry. Okay, so how are we evaluating ourselves on this task? Well, I said that we're making 514 different predictions. You can view those predictions as a big vector of numbers. And we're trying to, and Similarly, there's a big vector of ground truth numbers. So we'll call the vector of ground truth YT for any given target date. The vector of ground truth is YT. Our predictions are Y hat T. And we're measuring quality in terms of root mean squared error, geographic root mean squared error. So that's the average squared error across all grid points, square rooted. And I just want to highlight this is a multitask objective function. So it actually couples together the G different per grid point forecasting tasks because of the square root. Okay, so to tackle this task, we first needed some data. And so we formed what we call the subseasonal rodeo data set. We use this to train and evaluate our models. It's drawn from a diverse collection of data sources. It includes temperature data, precipitation data, but also pressure and humidity, some larger scale phenomenon like El Nino, the state of El Nino, the Madden-Julian oscillation, and even some coarse-grained numerical weather prediction forecasts. And we released that data to the Harvard Dataverse, so you can also use it to train and evaluate your own forecasting models. Roughly, the organization is as a set of Python pandas files in HDF5 format. We have spatial variables, temporal variables, spatiotemporal variables. All the spatial data has been gridded to a 1 by 1 degree grid. Most of it has been restricted to contest grid points, but not all. And all the measurements have been replaced with either averages for temperature or sums for precipitation over the ensuing 2-week period. So on top of that data set, we've built a diversity of forecasting models. And so here's a snapshot of a few of them. One we call climatology++. It's a relatively simple model and predicts the mean or geometric median observation in an adaptively selected window around the target date. So it's a locally constant prediction model. A second is a neural ensemble model. It's an ensemble of a large number of randomly hyperparameterized neural networks that use sea surface temperatures as input. We have what we call CFSV2++. This is a learned correction for that operational physics-based numerical weather prediction model that I mentioned earlier, but that often performs much better than the original. And then also Persistence++. It's a learned combination of physics-based forecasts, lagged measurements, and climatology. And what we found is that typically in any given year, at least one of these models performs quite well. But as you can see, the model forecasts can differ considerably, and it's often not clear which model is going to perform the best in any given year. Here you can see that climatology++ performs best over just a 10-year period. There's a diversity in the quality of these models. So that leads to an important question. How do we choose a single forecast to issue each day if we're doing real-time forecasting? And I think, as you might imagine at this point in the talk, our answer is going to be online learning with optimism and delay. So in particular, we'd like to select a set of weights, these are the WTs, lying in the simplex, so that we can predict a convex combination of our input forecasts. So if we think of the forecasts as columns in a big matrix, Y hat T, then we'll use this WT to combine those columns into a single forecast. And our goal is going to be to perform nearly as well as the best model each year in 2011 through 2020. We're going to adopt as our loss the RMSE loss that we already described, now parameterized in terms of this vector W. And we're going to evaluate each of the algorithms that I introduced, DORM, DORM+, and AdaHedgeD. Now, since we're operating with optimism, we need some hinting strategies. And so for that, we've adapted several common hinting strategies that are often used in the undelayed optimistic online learning literature. So first is the none hint, that is, don't hint at all. There's also the PrevG hint, which is, since we're trying to predict the next, the D+1 missing gradient, we're just going to use the last D+1 subgradients that we've observed. There's a mean G hint, which takes the average over all the subgradients we've observed and then replicates that d+1 times. And there's a recent G hint that just replicates the most recent subgradient. So for most of the results that I'll present, I'll be using the recent G hint, but I'll also show you a comparison of these different hinting strategies. So first, let's just observe what happens on average over the 10-year period of interest for us. What we see is that the online learners, each of the online learners, AdaHedgeD, Dorm, and Dorm Plus, compares favorably with the best input models and in line with our goals. And also, these models learn to downweight lower performing candidates, the worst models that I'm highlighting in red. So in this table, in blue, I've highlighted the best performing online learner and also the best performing model. And in red, I've placed the worst performing model. And what we can see is that, in fact, Dorm Plus, the best performing online learner, actually outperforms the best model in 3 of the 4 forecasting tasks. And all 3 of the algorithms outperform the best model in the precipitation tasks. So that's great. And we see similar behavior when we examine performance year by year. Now, you might be wondering, how do you read a table like this? So how do you read a plot like this? Let's zoom in on a particular year so I can explain what's going on here. What I'm displaying is the average regret over time as the year progresses. And this black line represents 0 regrets. So if you're on the black line, it means your performance is exactly matching the best model, the best input model. If you're above the black line, you have positive regret, so slightly worse performance than the best model. And below the line is negative regret, actually doing better than the best model. And so you see here that each of our 3 algorithms starts out with negative regret, has a period of positive regret, but by the end of the year, all 3 have negative regret. So they're doing better than the best model, the best input model. Now, zooming back out to this yearly plot, we see that actually year after year, we're observing small average regret, despite only having 26 observations per year. That's very much in line with our goals. And in fact, in several of the years, 2011, 2012, 2014, 2020, for instance, we're achieving negative regret, that is better performance than the best input model. Now let's turn to let's explore a bit the impact of regularization. We spent a good bit of time discussing what could happen if you used an overly conservative setting of your lambda parameter. So let's see what happens in practice. Here, we're going to compare the evolution of the regularization strength and the model weights for 3 different algorithms. There's the self-tuned Dorm Plus, so actually that doesn't even have a regularization parameter. There's a tuning-free Dorm Plus that doesn't even have a regularization parameter. But then we also have the self-tuned algorithm, AdaHedgeD, and a third algorithm, which we'll call Dub, which is a more conservative tuning strategy that's based on a much looser regret bound. So what do we see happening in practice? Well, on the left, you can see the regularization parameter growth for AdaHedgeD and Dub over the course of a year. And we see that the Dub regularization parameter is growing much more quickly than AdaHedgeD. And by the end of the year, it's over 40 times larger than the AdaHedgeD regularization parameter. And what does that imply for the weights that are played over time? Well, you see that the Dub weights barely deviate from uniform because the regularization strength is so large. This is the impact of having these overly conservative lambda settings. Meanwhile, both AdaHedgeD and Dorm play much more adaptive weights and hence can adapt to the changing quality of methods much more rapidly. Now we can also explore the impact of our optimism strategies on regret. And recall that we've been studying 4 different optimism strategies: none, mean G, prep G, and recent. We find that none is actually, which I mean, not using any hinting, is outperformed by all the hinting strategies except for mean G. So that's promising. We're seeing the benefits of actually using hinting for the future and missed feedbacks. And we also noticed that recent G performs best on all 4 of the tasks. I'm just showing you a display from precipitation weeks 3 and 4, but recent G is the top performer in all 4 tasks, at least when combined with the Dorm plus algorithm. Now you might wonder, how do you pick one of these hinting strategies in practice? And we've wondered exactly the same thing. And so this is the solution that we've come up with. We call it learning to hint with delay. And it's based on this observation. It turns out that Dorm plus, and AdaHedgeD all admit bounds of the following form. That is, you can bound the regret of each of these algorithms in terms of a sum of convex hint loss functions. So loss functions that you can view as functions of the hint vector that are convex in the hint vector. Here's an example. For the Dorm algorithm, you could choose essentially the norm discrepancy between the hint and the last d+1 gradients. It's not exactly the gradients, it's this R vector that's a small transformation of the gradients, but you can think of it as hint vector minus the last d+1 gradients. And once you've written the regret in this way, well, a natural thought is, why not use online learning to learn how to combine different hinting strategies? So if I have, for instance, 4 different hinting strategies and I don't know which one to choose, let's learn how to combine them over time adaptively. And so in particular, we're going to take all of our different hinting strategies, stack them up into a big matrix, let's call that HT, and we're going to form a combination hint, which is a convex combination of the columns in HT. Well, it turns out this can work. If your base online learner satisfies this regret bound property, then learning to hint actually offers the following regret bound, which says that your regret is nearly as good as the best constant hinting combination in retrospect. So it can perform at least as well as like the best hinting strategy and even the best combination of hinting strategies in retrospect. Great, so if we go back to our impact of optimism plot, we see that, well, recent G is definitely the dominant task, but year after year, there's also a learned line on that plot in blue, and year after year, our learning to hint strategy provides a competitive default that is typically maybe a bit worse than recent G, but often much better than the worst options that are out there. So let's summarize what we've accomplished. I've introduced these 3 new algorithms, Dorm plus, and AdaHedgeD, that have optimal regret under delay, that incorporate hints for missed feedback to mitigate the impact that we saw from delay, that have no hyperparameters to tune, and that can be used in combination with this learning to hint wrapper to learn effective hinting strategies. And I thought I would leave you with a few open questions and ideas for future work. So first, regarding hinting with delay, a great question is, what is the relative impact of hinting at the future versus hinting at missed losses? In the appendix of our write-up, we do a small exploration in this regard. I'm showing you a plot from that exploration here, showing you how much your RMSE decreases for each of our forecasting tasks when you just hint at the past, when you just hint at the missed losses, when you just hint at the future losses, or when you hint at past plus future. And you can see, or even use stronger hints, and you can see very interesting patterns there. But I think there's much more work is needed in that regard. And along the same lines, are there optimal or near optimal hinting strategies under delay? And can we learn them? Another open question is whether we can develop tighter convex regret bounds to use inside of this hint learning framework. And we'd love to incorporate more domain-specific hinters. So far I showed you somewhat generic hinting strategies, use the previous gradient, use the average of all gradients. But in subseasonal climate forecasting, we have access to shorter-term forecasters that can provide more accurate predictions of missed losses. Because of delay, a missed loss is, a shorter horizon into the future. And so you can imagine predicting it more accurately over time. So I'd like to just leave you with those few ideas, and I encourage you to check out our our write-up on archive, and our Python optimistic online learning with delay package on GitHub. Thank you for your time.